Let's have a look at 12 in our series from this chapter 3 on entropy. And it's asking us to, in part A, calculate the change in entropy of the system when 10.0 grams of ice at minus 10.0 degrees Celsius is converted into water vapor at 115.0 degrees Celsius and a constant pressure of 1 bar. That's standard pressure, 1 bar. Sorry. The constant pressure molar heat capacity, the ones that we need are given. So for solid and liquid water, we're using the same value, 75.291 joule per k-mole. And for vapor, 33.58 joule per k-mole. All right. Let's sketch this out. This question is really all about picking a convenient path and breaking up one big process into ones that we can solve, and then adding all the values of delta S together. We can do that for entropy. We can do that for things like entropy or enthalpy or internal energy, and just break down the process into steps, because these are state properties. And so let's go right across the page here with what's happening. First of all, I have ice, so I'm going to put H2O solid, and everything is at constant pressure, so maybe I'll just umbrella that in. Excuse me. It's 1 bar exactly, that's fine. Okay, so H2O solid, we're starting at minus 10 degrees Celsius. It's given with 3 significant figures, and it's heated all the way to 115 and therefore vapor. So we want to break this up into, what do you think are these processes? It's constant pressure, so it's constant pressure what? Constant pressure heating. Okay. You don't want to enter into a situation where your heat capacity of the material is changing. So the bracket of, for this broken down step is determined by heat capacity bookended by any phase transition. So if I heat ice from minus 10, I'm going to run into a phase transition at 0. So that's why I want to just heat my ice and not change the phase. Keep it ice, so that's why I continue to write solid, but I bring it all the way to 0 degrees Celsius. And I have a constant heat capacity in this stage. And the constant heat capacity over this range, I'm just looking back at the question to find it, 75.291 joule per k mole. Okay, so that's the first step, if you like. And you can write them underneath each other. I'm going to go across the page. Excuse me. So now what? If you were writing underneath, I would repeat H2O solid here as the first state of the next process. And so we heat it right up to 0. It's still a solid. At 0, it's going to melt to the liquid. Keep that temperature constant. So now, actually, you know what I'm going to do? Under this arrow, just label the process for you. Again, because it's a tutorial, this would be constant pressure or isobaric heating. All right? And over here, this is a phase change. And it's a phase change from the solid to a liquid. And as a phase change, it's therefore occurring constant pressure and temperature. The temperature of the phase change, in this case, the melting point. Okay, now that I have water, liquid H2O at 0, I have to get to vapor at 115. So slide this over. The next thing then that I want, how about we do this? The next thing I want to do is heat the water. And where are we going to heat it to? Until what temperature? I don't want to go past a phase transition, so my next phase transition then, this is the whole stability of the liquid phase range, so I can go all the way to 100. And I'm using this 0 and 100 almost as a label, but because minus 10 was given to 3 sig figs, I'll use that as my guide for how many sig figs I want. So now I have water at 100 degrees Celsius, and again, this process here is a constant pressure heating, and I'm still going to use the same heat capacity because I'm instructed to. Although I'm wondering about that. So that's that path. And then I have another phase transition. I'm going to shorten my arrows here to fit everything in. You can put gas or vapor, it doesn't matter. It matters that it's the same temperature. So here I have a constant temperature and pressure boiling or phase transition more generally. And finally, I'm going to superheat this vapor to a temperature of 115. Constant pressure heating again. This time of the vapor. Different heat capacity, 33.58 joule per K mole. And that is the molar heat capacity of the vapor. Whereas this one was the molar heat capacity of the liquid. And I'm instructed to use this as the molar heat capacity of the solid. All right, so now I'm just to keep things organized, I'm going to label this step 1, 2, 3, 4, and 5. Okay, 5 over there. And we'll continue with calculating the delta S in each case. So, again, I'm hoping that you're going to be looking at these questions in series, in order. So I don't want to start all the way back at ds is equal to dq reversible over temperature and move forward. I think that we can jump to the formula, and if you're not at that stage, then review what comes before question 12. Do these in order, be a bigger benefit to you. So constant pressure heating, delta S for this step is number of moles, N Cp molar ln T final over T initial. I'm not going to go through with the numbers on this one because the number of moles, well, I think we're given a number of grams. Yeah, 10 grams. So why don't I scoot back here for a second and just put this in 10 grams of H2O equals my sample. Okay, so determine the molar mass of that, and therefore you have the number of moles. The heat capacity is this guy, and the ln T final over T initial. And in case you have the sound off, I still want to warn you that this has to be input as Kelvin. Of course, the units cancel, But if you, shame to get that wrong by putting it in as a Celsius unit. So don't do that. Your units will be, moles will cancel, joule per Kelvin for number 1. In number 2, we have a phase change, and that will be equal to simply delta H over T, right? And we have the delta H of vaporization. It's given per mole, and we have the melting point. Well, we know that it is 0. So a couple of things here. Of course, this will be Kelvin. It's a nice flag there. It goes up when you try and divide by 0. So I don't think people would make the mistake of using Celsius. And notice here that, in the end, the goal is to add, excuse me, all of these together to get delta S for the whole process as 1. And of course, you'll have to add apples to apples here. In other words, these have to have the same units. N is in moles. This is joule per K mole. The moles will cancel, and I'll just be left with joule per Kelvin, which is correct. At the moment, this will be in joule per K mole, because delta H is joule per mole. So don't forget that this is specifically not a, this is specific to this 10-gram sample. So you'll have to determine how many moles 10 grams is and multiply this here. That way you've got joule per Kelvin as units, joule per Kelvin as units. In the third step, again, once I've phase transitioned to the liquid, now I'm just heating the liquid. So delta S in this third step is N number of moles times Cp molar for the liquid. That one was for the solid, this one's for the liquid, ln T final, T initial, and my units have to again be in joule per Kelvin. Sorry, I'm losing my voice. 10 grams converted to moles, molar heat capacity for the liquid given in the question. Ln of T final over T initial. The T final for number 3, that's where we were heating the liquid just up to 100, but not including the phase transition yet. That will be subsequent. So this is 373 over 273, etc. The second to last step is the phase transition. Oh, can I move back here for a second? Sorry, I'm so used to vaporization. This phase transition for number 2 is not vaporization, but rather fusion or melting. Sorry about that. And sorry. Okay. And then this phase transition, yeah, we're not boiling water at 0, but we'll boil water at 100, so that's where this one is. Now it's delta H vaporization, sorry, over T boiling, if you like. I was going to put T vat, but it's boiling temperature. So the boiling temperature, we want to input that as 373, our heat of vaporization, molar, and then the number of moles, so that moles cancel, and I get an answer in units of joule per Kelvin. Now my last, yeah it is, my last step is a constant pressure heating of 10 grams of vapor. So again, converted to moles. Molar heat capacity this time for the vapor or for the gas, and that was the 33.58 joule per K mole. Ln T final over T initial in units joule per Kelvin. So 10 grams converted to moles. This is given. My final temperature is the Kelvin equivalent of 115 Celsius, and the initial is 373 units joule per Kelvin. When you do all of these, what you'll do is determine all of each of these, or all of these. You're going to add them all up. Fit that all in at once. And again, I'm not going to write total, I'm just writing delta S for the whole process, just delta S. And it's going to equal the delta S of 1 plus that of 2 and 3 and 4 and 5. And you'll have an answer again in joule per Kelvin. So I haven't actually calculated this, but I'm quite confident that you have enough here to check your own approach to this problem, and that you would be successful in doing part B once you understand A, because it's kind of a repetition. So now, a couple of comments on this question as we move closer to the exam. It's a great question. How do you think you could add to it? Make it a little more complex. Add a layer. Think about it. We went from a solid to a liquid to a gas. Maybe that gas could ultimately expand, and that would include another consideration for entropy. So that's possible. Maybe that gas could be compressed, in fact. Or if I compress or expand it, it could be done isothermally, in this case still at 115, or maybe the subsequent step would be an adiabatic change on it, compression or expansion. So just keep that in mind, because it really brings in everything that we've considered on these systems, and that's the nature of a final exam question. Going back to the process as a whole, we might consider the enthalpy change in each of these steps. And if we did that, it's a formula that's quite similar, you'll recall, to this one, except it's NCP molar, for example, in the first step. Instead of the ln of T final minus T initial, it would just be NCP delta T. So kind of like to put those calculations together to see how the enthalpy changes and how the entropy changes. Okay. And for this one, the in step 2, what would be the enthalpy change in step 2? Well, I have delta H per mole, and then I only have the number of moles that corresponds to 10 grams. So it would just simply be N delta H. Over here, N CP delta T. Over here, N delta H. And again, I'm just calculating enthalpy now throughout this whole big change. And finally, NCP delta T. So now I would have a lineup of all joules instead of joule per Kelvin, and add that up and get a total enthalpy change. And again, thinking forward to the exam, you can be asked, and we have been asked in these text exercises, to rationalize the answer. So that just means to explain why it is the way it is, whether it's really large, really small, negative, positive, that sort of thing. Okay? So it's a good question, and you should try part B.